We'll have an invited talk with Dr. Fee right now, and after that we will have a panel discussion with a group of international experts, which is going to be very interesting. And we have Dr. Fee coming all the way from Alaska to tell us a very interesting story. Dr. Fee, the floor is yours.
Yeah, thank you, Pierre. Yeah, and thanks for this opportunity to talk about this eruption, which is truly remarkable. This is a work done by a lot of people. It's really captivated, the interest of scientists and the public. I'll just be presenting really some kind of observations and preliminary modeling of the atmospheric waves from this eruption, which is, like I said, just truly remarkable. I'll probably be filled with superlatives as I talk. And I think you'll see why, and perhaps you already know. So this is work done by many. I want to acknowledge just a few co-authors here that I have listed on my title slide. But many other people have contributed to this work as well. I also want to acknowledge my funding agency that supported our work at University of Alaska Fairbanks, and that's Defense Threat Reduction Agency, NACT program. So kind of an introduction and overview of what I'll be talking about today. I think most people are probably familiar with the Tonga-Hunga eruption of in mid-January of last year. Like I said, this was really very exciting for both the scientists and the public, but I don't want to, of course, forget that it was definitely a hazardous eruption that caused, some significant ashfall in the region, as well as damaging tsunami waves regionally and tsunami waves observed globally as well. And when I talk about, what occurred, I think it's truly appropriate to say that this is a once-in-a-century atmospheric wave event, with really the only comparable event being the 1883 Krakatoa eruption. And I'll talk about some of the comparisons with that eruption as we go. So in my presentation today, I'm just going to discuss some aspects of the eruption signals. We'll talk about it more in the panel afterwards. And specifically, I'm going to be talking about those recorded on barometers, infrasound sensors, and seismometers. I'm not going to go too much or really at all into the eruption mechanisms, but perhaps that's something we can talk about in the panel. So as I said, this is work done by a lot of people. A lot of this was covered in a recent, or I guess last year's manuscript led by Robin Matoza. I say a lot of people, there were 76 co-authors, and I think that really is just a testament to how many people, I don't want to say were needed, but were really helpful to understand what went on, because it was surprising in a lot of ways, and it was recorded so extensively globally. So this was research that we completed in a very short amount of time, and it was highly collaborative. So I want to thank all the people who contributed. And again, I'm just going to provide a broad introduction to these atmospheric waves and the seismoacoustic signals, highlighting those that were recorded on the IMS network too, because those were very significant contributions to our understanding of these waves. And the figures that I'm going to show are from that manuscript, unless otherwise noted. And I encourage people to reach out and find other information on this eruption as well. So here's a chronology of the eruption signals recorded on the IMS network. So this is between December 1st, 2021 and February 1st, 2022. And so the top panel there are the hydroacoustic detections, so underwater. Then you have the seismic detections, and then infrasound. And the bottom is kind of the number of detections and infrasound over time. And this kind of gives us some insight into what occurred before the eruption and where the eruption was occurring. So the first handful of days of the eruption, we were recording hydroacoustic and seismic events, so the eruption was predominantly undersea. And then in kind of mid to late December, it transitioned to having subaerial activity, so it was also producing infrasound recorded at numerous IMS arrays, with IS-22 in New Caledonia recording it best. So after this kind of vigorous activity, it backed off in early January, and then picked up quite a bit on January 13th. And then the very large eruption that I'll be talking about for the rest of the talk today was on January 15th. And this was, again, notable for many, many reasons, but it was recorded across the IMS. It was the first event to be recorded on all 53 IMS infrasound stations. And just for people who aren't aware, we usually don't get large events in the atmosphere. We don't have earthquakes that are recorded globally in the atmosphere, so this was a really unique situation for us. So this is probably my least exciting slide, or I can guarantee it. This is just some terminology and definitions, just so people can be kind of familiar with what I'm talking about. So again, I'm just talking about atmospheric waves, but what was exciting about this, amongst other things, is that it produced all different types of atmospheric waves. And these are some kind of definitions to help kind of guide that. So we had these very low frequency gravity waves, and these are where we have a significant buoyancy component to those as well. And then above that, at higher frequencies, we have acoustic waves, which we're probably more familiar with. This is a pressure wave propagating through the atmosphere as a series of compressions and rarefactions. And in between those two, we have acoustic gravity waves, and it's kind of exhibit, both motion from both of those components. And these are frequencies, still kind of very low frequencies in the kind of millihertz range. And this is where the most prominent pressure wave from this eruption was, and that's a LAM wave. And this is a very large atmospheric surface wave that propagates, spherically across the globe. People may be more familiar with infrasound. This is what we kind of typically study, especially for the IMS, and this is frequencies of about 4 millihertz up to 20 hertz. And then above 20 hertz, that's where we get into the audio range where humans start to hear sound. And I will just note that usually we model and think of sound propagating linearly through the atmosphere with these kind of like linear models that we can understand. But there was a significant nonlinear component to the propagation as well for some of these waves. So here's a map of a number of things, but first, if you weren't familiar, Tonga is in the Southwest Pacific. Tonga is, it's a very remote area. It's been historically active in numerous eruptions. But it's, like I said, it's very remote, and we have these remarkable geophysical networks across the globe, such as the IMS, that we use to study this eruption, and then we supplement that with these kind of more dense regional networks. And this map, if you can see it, is plotting all the geophysical stations that we used in our study. It was literally, thousands of geophysical stations recorded this eruption, and more than I'm just plotting on this map. But we have seismometers, barometers, GNSS, we have undersea hydrophones as well. Also, what I'm overlaying on this, or we are on this plot here, is the eruption, the LAM wave, the pressure wave, is also observed clearly in satellites. And this kind of red and blue wave that you can see propagating out spherically is the brightness temperature difference observed in satellites, which was pretty amazing when you see these animations, or if you just see an image of this wave propagating in the atmosphere observed in satellites. The wave that I'm talking about here was also very notable that it traversed the Earth multiple times. So at least 4 times in one direction and at least 3 times in the other direction. And we have different ways of kind of classifying that and labeling that. So here I'm going to show an animation of the pressure wave, that acoustic gravity LAM wave, as observed in satellites propagating out. At the same time, I'm going to be showing the barometer data from the IMS and other stations, and as that wave is recorded. So showing a couple things here, assuming my animation plays. So you see, boom, there's the eruption. You can see the wave propagating out. You can see it really clearly on these dense regional networks in places like Alaska and in the lower 48 of the US. Now we see the wave propagating back the other direction that went around the other side of the Earth and is coming back towards the source. And it gets a little bit complicated. I'm going to play it again real quick so you can see the wave propagating out. And then the wave you see in the satellites agrees very well with what we observe in the barometers on the ground. So let's look at the data in a bit more detail. So here I'm plotting the global barometer and seismic wave observations. The top plot, what I'm showing, so these are the barometer data across the globe for 6 days, and from 0 out to about 20,000 kilometers. And you can see this really nice signal picked up for days. And this is the LAM wave propagating one way across the Earth, and then that kind of second branch going down is the wave going the other way around the Earth. And we can see this again globally for multiple days. The propagation velocity of this wave is about 315 meters per second, which is consistent with a LAM wave propagating out spherically. On the bottom plot, this is a stack of a whole bunch of global seismic data, all put together. Notice the time scale here is much shorter. This is only on the scale of hours, but we see some really interesting things in the seismic data as well. First, there's P waves produced by the eruptions, but then the kind of most prominent wave are these seismic Rayleigh waves, seismic surface waves, Rayleigh waves. You also see that there's this really slow-moving wave that we've labeled A1 here, and this is actually the atmospheric wave coupling onto the seismometers as well. So this is just kind of another hint at how rich this data set is in the waves that were produced. So let's talk more about the global barometer data, and in particular the amplitudes. So I've talked about all these different aspects, but of course it was very energetic, and it was very loud, a very big signal. So the plot on the left is using the global IMS barometers, and I'm plotting the amplitude, the peak-to-peak pressure on the y-axis on a log scale, and then the distance on the x-axis. What you see is we first have very large amplitudes, over 1,000 pascals at the nearest station, and we see the amplitudes fall off generally 1 over r, as we would expect for a spherically propagating wave. But as you get to around 7,000 kilometers or so, things start to get more complicated, and we see a significant scatter in the wave amplitudes. And I'll touch on this a little bit later, but that's likely, I think, related to some complexities in the propagation of the wave. What we also see as you get past like 10,000 kilometers is the amplitudes start to increase again. And this is because the wave is propagated around the globe, and it's a spherical Earth, and the amplitudes are getting larger as it refocuses in on itself. On the right here, we're plotting the amplitude, so those dots that I showed on the left, but we're also plotting barometer amplitudes from other very large explosions and historical data. So you can't read it probably, but we have megaton nuclear explosions in addition to the Hunga data. I should say the Hunga data, or the black circles, and then you can see again like these megaton scale nuclear explosions, atmospheric tests, and then some very large volcanic eruptions and bolides on there as well. So what's notable for the Hunga eruption is you see that first of all, we have a lot of observations. That shouldn't be a surprise. It just happened. We have a lot more instruments now. But also the amplitudes are very high. The only thing that really matches it is the 1883 Krakatoa eruption. And it's higher than any of the previous nuclear events or volcanic explosions, again, other than Krakatoa. So let's compare it a little bit more to that Krakatoa eruption of 1883. This is notable. I was always taught this is kind of the birth of infrasound. So although it was 140 years ago, they did have barometers across the globe, and they've done some pretty amazing studies like figuring out what happened and documenting it. So we compared the observations from the Hunga eruption with those from Krakatoa, and you can see in the top plot, these are the global barometers, observations for Hunga in black and Krakatoa in blue over a span of 6 days. And what we see that we have, again, pressure wave signals from Hunga for 4 days, four circumnavigations of the globe, and then 3 the other direction. And we actually have a similar amount in blue from the Krakatoa eruption. When we go and compare the actual waveforms, the barometric data from these two, that's what I'm showing on the bottom 2 panels from similar locations, they actually look pretty similar, which is interesting. So the amplitudes, these are the same amplitude scales. You can see they're essentially quite similar and with some similar features, but the Krakatoa duration of the signal was about 30% longer. And of course, we all know that our instrumentation networks are quite a bit different now than they were 140 years ago, but still kind of interesting to make the comparisons. One of the other things about this eruption I think is quite interesting, that it was so large and so energetic that it basically excited the atmosphere into resonance. And that resonance then coupled into the Earth and excited the Earth normal mode resonance as well. And this has actually been observed for some previous eruptions, but it was particularly notable for Krakatoa. So the plot I'm showing on the left, without going into all the details, in black is the stacked barometer data. We're looking at the spectra, or the frequency content, and then in blue is the stacked seismic data, and the top of that is the coherence between those two. And we have this notch in this one area at 3.7 millihertz. And what this is happening is, again, we have this energetic pressure source in the atmosphere causing resonance to set up between the ground and the mesosphere. So the Earth is shaking, and then that then couples into the Earth and causes the Earth to resonate. And the Earth resonates at 3.7 millihertz, and this was recorded very clearly across the globe on seismic stations, as shown on the plot on the right here. So we have this like fundamental mode of the Earth and then the first harmonic recorded clearly as well. I want to note that this, the Hunga eruption signal was actually 10 times larger for this 3.7 millihertz signal. And I guess the last thing is that this atmospheric resonance was also recorded on regional barometers for the first time. One significant aspect of the eruption as well is that the land wave and the atmospheric waves coupled into the ocean, and they contributed to the tsunamis. So what I'm showing on the left here, this is tsunami meter observations. So this is undersea, deep sea pressure wave data, and then you can see the associated waveforms. And you can see that the land wave in the air, as it propagated across the sea, coupled into the ocean, produced these very large, high amplitude pressure waves recorded at the bottom of the ocean as well. The amplitudes underwater were actually substantially larger than those recorded above ground, and they contributed, weren't the sole cause, but they contributed to the tsunami as well. And not talking about the tsunami much, but it was very interesting for this eruption because it arrived faster and was much more complex than expected. So I think there'll be a lot to study in that in the future. On the right-hand side, what I'm showing on this figure is some observations of a single above-ground sensor and then two sensors, pressure sensors, underwater in the Mediterranean in Italy. And so the pressure wave propagated from Tonga in the South Pacific all the way out to Italy and then coupled underwater, and it was recorded clearly. So I just think it's kind of incredible that it could do that. One other aspect of these pressure waves is the dispersion and how the different wave energy arrives. So this is data from IMS infrasound station I-59 in Hawaii. And this plot on the right here is showing the pressure data in different frequency bands. So the top is this kind of really broadband signal. That's kind of the whole pressure wave itself. And then the wave is then filtered in different frequency bands, getting to higher frequencies as you go. And this is to highlight the various acoustic gravity wave modes and some other features of the wave. And the first thing that I want to point out is that we have pressure wave or acoustic energy from 6,000 seconds all the way above 10 hertz, which is unprecedented. So that's kind of first and foremost interesting about this figure. We also note that the relative timing of the waves, so this land wave that propagates along the Earth's surface arrives first, followed by the infrasound, which was very energetic, and then you get to increasingly higher frequencies as well. So let's dig into those spectral properties as well, because they are so unique. So this is a plot of data from interior Alaska, actually, so about 10,000 kilometers away. On the left is a microbarometer, and then seismic to the right of that. And we see a number of interesting things, kind of consistent with the previous plot that I showed. But again, this incredibly wideband pressure wave data out to at least 50 hertz here. And it's very high amplitude even at 10,000 kilometers. And then the seismic data, we see a number of things here. We have the initial Rayleigh wave from the eruption, but then we have this multiple types of coupling from the atmosphere into the Earth. So I talked about the fundamental mode coupling earlier, but we also, as the land wave propagated across the seismometer, it coupled into the ground as well. On the right is a plot of the comparison of the frequency content from the Hunga eruption atmospheric waves compared to all previous events that have been instrumented. And you can see a few things. So the top are bolides in blue, atmospheric nuclear tests in red, IMS infrasound recordings, and then numerous large volcanic eruptions over the past 100 and some years. And what we know is, again, that the Hunga eruption spans all of these and is an incredibly wide band. This isn't to say that the Krakatoa eruption or maybe the Tall eruption wouldn't have something similar, but we have, of course, differences in instrumental networks that allow us to measure this now. So one of the things that I think is still kind of up in the air and looking at more is, so what's actually happening close to the volcano? Everything I've talked about before is generally thousands of kilometers away. Well, there's not a lot of data nearby, but there was a local barometer about 68 kilometers away. And I'm comparing that in this plot here with another barometer about 1,500 kilometers away. And first, you notice that they look really similar. The features of the pressure waveform looks very similar. But what I've done is I've actually taken that the blue trace, the barometer, and I've flipped the polarity. I've multiplied it by -1. Because when you look at that barometer data, it actually starts with a decompression. And this was, I think, pretty interesting to us when we first saw this, is that it's a big explosion. You expect an increase in pressure nearby, but the closest station actually has a decrease in pressure. It turns out that this has been observed for other large volcanic eruptions, such as Mount St. Helens in 1980 and Tala in 1911. And so what's going on here, one of the hypotheses is that you get this large eruption and this plume going up, that it's entraining and kind of sucking in a lot of air and causing a decrease in pressure. But I think this is still kind of an open question at some level. I also want to note a couple things, that this isn't like a very simple waveform. It doesn't look like a typical explosion that we see. It's very complicated. It has multiple kind of bumps in it, so it's multiple pulses. And the onset is also, I think, fairly difficult to determine. The other thing, just from a terminology standpoint, it has a very slow rise time, not like a shock wave. So it's been called a shock wave, but I think it's probably more appropriate to not refer to it that way. So of course, a relevant topic for CTBT and for this meeting is yield estimation. And I think this is a very active area of research, and there's probably some good discussion that we still should have on this topic. And there's been some really good previous work looking at atmospheric explosions from kind of megaton scale nuclear tests and deriving the equivalent acoustic yield from that data, and specifically this Pearson-Posey work that I'm talking about. And this is the figure that I'm showing on the left, where they have these pressure data from these historical megaton scale nuclear tests, and then they derived a relationship to fit that data. This is based on the energy release and the peak pressure and the peak-to-peak duration of the signal. But when we did this for the Hunga eruptions, what we found that it produced unrealistically large yields, basically a couple thousand megatons. And this is primarily because the dominant period of the Hunga eruption is like 3,000 or more seconds. It's almost an hour long. And I think this gets back to the difference between this eruption and eruptions like this that have a very complicated and extended source time function compared to nuclear explosions, which are essentially instantaneous. The source area of this volcanic eruption is likely very large as well, and it's not just a point source. Also, just to note this, decompression that I showed in the previous plot, I think kind of complicates the source of what this is. But I think this is something that we should keep digging at and kind of trying to understand. And I will note that other studies have looked at this in a number of different ways and estimated equivalent yields in the 100 to 200 megaton range. So I'm from Alaska, so I'm slightly biased, but I also think we have a pretty good geophysical network, and I want to highlight some of the features that we recorded in Alaska. So I'm going to play a little animation here in a second. We have roughly 100 geophysical stations with, with barometers, and I'm going to play that barometer data over time. So on the top is just this is like, I think it's 17 hours or 24 hours of data. I'm going to try to play an animation. And what you're going to see is the wave is going to propagate from southwest to northwest across the state. Hopefully you saw it right there. The red is the compression, the blue is a rarefaction as recorded across the state. And in a second, you're going to see it come from the northeast down to the southwest. And there it is. And this is the wave going the other direction around the Earth and crossing the state. And you can see that as this wave propagates across the state and multiple times around the Earth, that we get lower amplitudes and more complicated waveforms as it propagates. The other thing that we noticed in looking at this kind of regional scale data, which I think is really nice to supplement these global networks like the IMS, is we start to see these kind of small scale or smaller scale deviations and kind of curiosities. So I'm plotting the peak-to-peak pressure amplitudes recorded in Alaska, and they vary between about 100 and 300 pascals. And this is at the same distance we can have a variation, between 100 and 300 pascals. And there's kind of a notable east to west trend, or I guess west to east trend in the data. And these deviations basically are not explained, at least simply by the modeling. So we need to come up with a better model to explain what's going on here, whether that's, the source doesn't radiate sound equally in all directions, or perhaps we have some very strong atmospheric variability that's affecting things. So talking a little bit more about infrasound, and specifically the IMS infrasound network detections. What I have here is a nice figure from Vergoz et al. Published last year, showing the detections on, again, all 53 IMS infrasound arrays. And you can just, these are the pressure waveforms over a span of a few days. And you can see the pressure wave propagating clearly across the network. And what's plotted in color there are the back azimuth deviations. So we have arrays, and we can determine the direction that the sound is coming from. Close to the source, it generally agrees with where we would expect, but as you get kind of further away and some more propagation over places, like the circumpolar vortex, you get these really large deviations in the back azimuth. And that's shown by this figure on the right as well. So this is the I-37 array in Norway. We can see these, very energetic, very clear signal. The back azimuth starts pointing at the volcano, but then it drifts by tens of degrees over a span of hours. Another thing, and this is kind of a point of future work that I'll just touch on here without going into too much detail, is modeling the sound propagation across the globe on the IMS. And I think this is, again, an area of future work where the models don't explain the observations very well at this point, and it's important for us to understand that. So on this plot on the top left, this is the effective velocity ratio, kind of a proxy for how well the sound should propagate. And then we have the attenuation, the sound pressure loss in that center plot, and then the actual observations on the right. And probably a little tough to see right here, but I'm showing a couple of examples down on the bottom as you look at that predicted attenuation. And what happens is that it explains it well in some locations, but in a lot of locations, the modeling basically doesn't match the observations. And the amplitudes that we record, I think, are in general much higher than the actual observations. So this is important for us to understand from a CTBT perspective as well, as we want to understand the source and the propagation. So kind of the last thing I want to talk about all these different types of waves. Probably the most interesting to me, because I heard it, was the audible sound from the eruption. So this eruption produced all this amazing sound waves, and it was actually heard at these just incredible distances. It was heard by numerous people in Alaska at over 10,000 kilometers. There was recently a paper published by Kraft et al. Actually documenting audible sound from this eruption at over 17,000 kilometers, which I didn't think was possible. So the audible sound from this eruption occurs after this LAM wave. The figure that I'm showing here on the left is a spectrogram, the sound energy as a function of frequency, and you can see that the sound energy from the eruption goes well into the audible. And this is consistent with, again, people who heard the eruptions, which sounded these kind of repetitive booms. And the same was reported in Central Europe as well. So explaining these observations is a bit tricky, as in I don't think we really can right now, although we have some ideas, but I think that's definitely an area of future work. And I think it's also interesting to note that this is the furthest documented audible sound, and yeah, so that's pretty incredible. So I'm just going to sum up here, and then I know we're going to have the panel in a minute where we can talk about a lot of different aspects of this eruption. But I just wanted to highlight some of the observations and kind of initial modeling of this signal. Again, it truly is a unique and incredible event. I think it's a global global benchmark data set across this incredibly wide frequency band. I want to highlight that IMS was really key to our observations and in understanding this, and I think probably the other way around, this eruption is really key to help understanding the performance of the IMS and the signals that it records. And we kind of detected, and looking at all these different wave types and way the wave propagated, that we really didn't have observations of before. And this is this very large and energetic LAM wave that was recorded so extensively, really energetic infrasound and these back azimuth deviations, et cetera, and this then higher frequency audible sound too. So I think there's a lot of areas for future work. There's already been a ton of work done on this eruption and the signals, and I'm looking forward to hearing more about it. So, thank you.